Okay, so our next last speaker in this session is Hoa Bui from Curtin University. So Hoa, please go ahead.
Thank you very much, Vera, and especially all the organizer for keeping this workshop annually. I would like to take this opportunity to express my gratitude to Ascendon Chat, because on those, we don't have any joint publications, which we all actually almost have. But Asen is my first friend academically, because I first met him in 2017 when I first came to Australia, and he came to Australia to visit Alex as well. But he secretly told me that he just came because of Australian Open. So it's still a secret from Alex. So we went to the zoo together. So this is a photo I took for him, and then he took for me. So we became friends since then. And then I met him many times, and I took so many photos for him, for Asen, but unfortunately we didn't have any photo together. So the closest one that I can find is this one that we in the same frame with Scott. So we look very serious. I really like this photos a lot. Okay, so yeah. So now back to the serious stuff. So so now I'm interested in solving a nonlinear binary problems. The reason for that is that because when you do many real applications like scheduling in industry, it happens that most of our variable is binary or discrete, and we have to deal with non-linear functions. So now I'm trying to find a way to solve a nonlinear binary problem where the variable is binary, and then all of the constraint. Okay. So we try to maximize the nonlinear functions over x belongs to k. K is a polyhedral set, or so the polytopes defined by intersection of closed half space. And then the function g, j here may not need to be linear, maybe not convex as well. So in the literature, there are two common approaches that provide a general framework. The first one is branch and bound, because branch and bound offer very general natural generalizations from linear to nonlinear, because the branching process actually doesn't require linearity, but the bounding may need. So the lower bound is actually the value function at the node that we're considering. But then in order to obtain the upper bound, we need to solve a relaxation problem. Here is a nonlinear relaxation problem. So there are two problems. The first one is that you may not, the solving a nonlinear relaxation problem may be very difficult. The second problem is that when the problem is non-convex, so it's sometimes impossible to find a global optimal value. So if you approach by using the approach by solving a dual problem, then you don't have the zero duality gap. So there's so branch and bound also have some drawback. So after approximations is another successful approach, which essentially avoids solving a nonlinear relaxation problem by approximate the nonlinear function or nonlinear constraint set by a collection of linear functions. Okay, so I visualize here. So for example, you have a convex constraint, and you try for outer approximation, you try to approximate this constraint set by a collection of half space. So with this approach, your region and your function require to be convex, because the only function or the set that is approximated by a collection of linear functions are convex. But a similar approach is a cutting plane. So the cutting plane idea is actually the ideology behind cutting plane is different. So they also use the hyperplane of the cutting plane, but not to approximate the region, but to remove non-optimal solution until the optimal solution is found. What this idea is offer you a more flexible approach. The first one is that your region, your physical region, doesn't need to be convex. The second flexibility is that you actually don't need to have the tangent. These are tangent plane, like as in this example. So you have way to modify your cutting planes. But for the cutting plane methods, in order to guarantee the convergent to optimal solution, so you have two key assumptions, two key conditions. The first condition when you design a cutting plane algorithm is that each cutting plane must remove at least one infeasible or non-optimal solution out of the search regions. So in other words, that cutting plane method is exhaustive search methods. And in order to guarantee, so the first condition guarantee the finite termination of the method. But for the second conditions is that because it's highly likely that if you don't be careful, the cutting plane may remove optimal solution. When it removes all the optimal solution, then the convergent point is not optimal solutions. So you have to make sure that each cutting plane must not remove optimal solutions. So as long as you satisfy these two conditions, then you'll find the methods converge finitely. So first of all, let's answer first the question that which cutting plane should we choose? So the first cutting plane we think of should be the tangent planes because this is the easiest easiest form. So let's forget about what happens here. So the nonlinear problem can be solved by solving a sequence of auxiliary linear problems. So this inequalities, this is cutting plane is called optimality cut. So to see here is a feasible set or a subset of feasible set. For any point in the subset of feasible set, you generate a cutting plane. It's called optimality cut. So we want to have each cutting plane rule out at least one solution. So for the optimality cut, you want to rule out the non-optimal solution because then this cutting plane will guarantee that whenever you are at current solution, if this solution is not optimal, then it won't appear again in your search space. And the second cut is related to G. G is the constraint functions. So for any point that's not feasible, then you create a feasibility cut. This feasibility cut will cut out the current solution that you are at to remove that out of the search regions. So in other words, each cutting plane will rule out at least one solution. So so the first condition for the cutting plane approach is guaranteed. But the main question is that how to choose C or C bar, which means that how you choose the cutting planes. So because for outer approximation, you try to approximate as best as possible. But this one is that the idea is that we don't need to consider all of the cutting plane. We only need to consider sufficient cutting planes. So, but if we consider C as a whole feasible set, so all of the cutting plane that the optimality cut that we can consider, and X bar is a complement of it, of K with C, which is all of the feasibility cut that you can consider. Then the value of the linear functions, optimal value of the nonlinear function is bigger than the value of the linear problem that you are considering. So which means that when you have the strict equality here, which means that your cutting plane has already removed all of the optimal solutions, which is not a good sign. So we need the following conditions that the two problems must have the same optimal value. But you may question that, how do we know that this happens? Then we have some other condition later, but let's assume first that you have this one first. So in this case, any set C, which is feasible, and any set C bar, which is not feasible solution, we provide an upper bound. Solving the linear problem, we provide an upper bound for NP. So that's why the standard approach for cutting plane algorithm is to as follows. First, you start 0, and then you update upper bound, lower bound, and then you choose a feasible point. And then you add that feasible to CK, so which means that you generate a feasibility cut, a optimality cut to check if X case is optimal or not. And then you check the stopping condition is that upper bound equal lower bound. And then you solve the linear problem to obtain XK, theta K, to obtain another solution. And then if this solution is infeasible, then you generate a infeasibility cut feasibility cut if this solution is not feasible. If feasible, then you generate an optimality cut and update the lower bound and upper bound. Under condition star, then the methods of course converge finitely. Well, then when conditions start hold, let's first think about why we have the algorithm converge to optimal solution, because there remain an optimal solution that is in the search region, which means that there is an optimal solution that satisfies all of the cutting plan. Well, this condition is still very impossible to check, because how can you know X star if you know it and what the point to solve the problem? For the special case when F and G are convex, or even more special that F and G are literally continuous and robustly quasi-convex, then this condition hold. Of course, for some other special problem, you can prove that the conditions that hold as well. So because I promised that from last week that we have some discussion on optimality conditions, because cutting plan methods actually using the 80 to 60 by Gonstein to solve a convex problem, convex programming, and the convergence point are stationary points. So that's why we may ask a similar question, that is there any optimality-like conditions for this algorithm applied for discrete domain? So of course, we don't have a very exact optimality conditions, but we have something similar. First is that if the derivative of the function f at our current iteration xk is small enough, so small enough in the sense that m1 minus m2, m1 is the best optimal value and m2 is the second best optimal value, and then divided by square root of n, then xk is optimal solution of np. So, but the algorithm may not yet converge because the optimality condition may not, the stopping criteria may not satisfy yet. So this is a drawback of this algorithm in discrete optimization. That even if you add a optimal solution, you already consider an optimal solution, the algorithm may take many steps until it's converged. But if the derivative of the function at our iteration xk is 0, then the cutting plan algorithm will converge in the next step. So which is good. And even better that if our objective function is quasi-convex. So because I know that my talk will be after Vanessa, so I think I will take advantage that everyone already know about quasi-convexity. So if the function f is quasi-convex and xk is optimal, which means that it satisfies the first conditions, then the cutting plan will converge in the next step. So we have some similar conditions like that. So let's move to the second part, that because I claim that for cutting plan we can easily modify. So how we modify cutting plan? So we modify cutting plan by changing two key items. The first one is b, because a is just a variable, and second is a. So we either can change a or b. So let what happens if we change b. So if we remember that for the tangent plan, the function z here is actually fy. So now we replace fy by some other functions, as long as the optimal solution of np is optimal solution for this problem. Then we can reuse this cutting plan, and for similar for the tangent plan for the constraints function, the constraints functions, we can replace zjy by gjy by zjy, as long as any feasible solution for gjy will be infeasible for zjy. So then we can reuse the modified cutting plans. So so the modified cutting plan methods can apply the same. You only need to replace the old cutting plan by the new cutting plan, but with one different, that is a stopping criteria. Because the stopping criteria is lower bound equal upper bound, Now the lower bound, upper bound, we don't know. There's no relation. So we replace that one by another condition is that whenever the algorithm repeats the previous step, which means that there's no other cutting plan generated, which means that you have to create loops. Then when you create the loops, then your algorithm must stop. So with the new cutting plan, modification, then the function f and g, it has a minor condition, which they only need to be pseudo-convex. And then the modified cutting plan with z is z and zj y is actually set the constants. Then the modified cutting plan algorithm still converge to an optimal solution. Well, and then okay, so actually now the changing the component A. So changing the component A is actually quite a convexification, because A is actually we choose that the derivative of the function f at the point at some current solution. So when you change A, which means that you change the curvature of the functions. And for convexifications, if you see here that because we are considering a binary solution, so xi minus xi squared actually 0. So by adding this term, these two terms, we don't actually change anything, any value of the function f and g, but we only change the curvature of the function f and g. And then if you, this is very elementary in convex optimization, that if you increase mu and lambda big enough, these two functions the f will become concave, or minus f will become convex, and g will become convex as well. Then we can instead apply the cutting plan algorithm to this nonlinear binary problem, and then you will converge to an optimal solution of the problem, the modified problem, which is equivalent to the previous problem. So you can still use cutting plan algorithm to solve any binary problem, but it's actually too good to be true, because but actually you have to be very mindful that don't over convexify, because the conversion rate of how good is your cutting plan depend on how you convexify your problem. Because if you have xk at your current step is feasible, which means that you consider you add a optimality cut, and your how good is your cut will depend on this ratio. So if this ratio is bigger than a square root of n is some natural number from n to n minus 1, small n is a dimensional problem that we are considering, then optimality cut will remove at least that many amount of binary solutions. So if we go back to convexifications, we didn't change the value of the function f, we changed the curvature. So which means that the denominator of this ratio is still remain constant. But what we change is we change the denominator of the ratio. So if this non-derivative is too big, then this ratio is too small, and then n will decrease. When n decrease, then you remove fewer solutions. So your cut is not tight anymore. So don't over convexify. So of course we have to test our methods by the standard classic quadratic knapsack problems. So the problem we consider is the quadratic problem. So with the knapsack conditions, so Q is a symmetry matrix with 0 diagonal. So which means that it has both positive and negative eigenvalues. So it's not convex or concave. But the cutting plan algorithm will still converge if your initial point still a full knapsack, which is that this is such equality happens, and then the Q is conditionally negative definite, which means that this is negative, or actually this is concave over this hyperplane. Or Q, in other words, Q has exactly one positive eigenvalues, then the cutting plan algorithm converges. Well, we generate random data because for standard test for quadratic knapsack, they usually randomize data, and Well, and Q actually has a special structure. So it is conditional negative definite. So that's why we need to find a way to generate it. So actually Q is a square of the mutual Euclidean distance matrix of n point in any finite dimensional space. And then we generate the test instant. And then we choose a range is large. Well, and then the matrix is full, is dense, 100% dense as well. And then we test with the IBM simplex and Glover linearization, because for solving quadratics programming, a very natural approach is linearize the problem. And for linearization, the Glover is much better than standard linearization. So we choose to benchmark with this one. And we set the time limit at 200 because the cutting plane method is only take 10 seconds to run, but the rest of them is take very heavy computation. So this is a graph. So the time for the cutting plane and the gap is for this one is 0. But for simplex and Glover linearization, Glover did actually better than simplex in terms of running time and provide optimality gap, because when I set the time limit is 200, so I have to bring out the optimality gap as well when I set the time limit. We have a vague idea why simplex perform bad, because actually it's happened that they over convexify, or they may use the standard linearization, because the documentation is not very clear which approach that they are using. Now we did also test for high dimension, and then, well, the graph is look better. So it's proportionally increased with the dimension. With this one is 50 instant each dimension. So you can see the proportionally increasing. But when I test for higher dimension, it takes like 2000 for the largest one. But if you can observe here that the time is not only depend on the dimension, it's also depend on the number of iterations. So because I only generate 10 for instant for each dimension, so it's really not really very uniform increasing. So you can see the drop in time here is actually the drop in the number of iterations for the cutting plane algorithm. Oh, thank you for your attention.
Thank you very much, Hoa.
Thank you.
Are there any questions? I'm not. Everybody is only uploading. Oh, Julien.
Hi,
Yeah.
Julie.
Thanks for the nice presentation, Hoa, very interesting. I have a quick question regarding the convexification, which you identified as a problem numerically.
Yeah. For simplex one.
Yeah, because in a little bit earlier you had a previous slide where you and I'm wondering whether you can actually have a different convexification at different iteration of your algorithm, since you're just cutting your feasible set. You don't actually have to cut using the same function, do you?
Yes. So actually our next it's our next step is just we will convexify every step that we we update delta mu and lambda, so that at every step we obtain different one. So when it is small enough, then we have a tighter cutting plane. So, yeah, so this is our next step.
Right.
Yeah, thank you.
Thank you.
Any more questions? All right, we don't have any more questions or comments. So I don't have any questions this time. So thank you very much, Hoa, for a very interesting talk. And I guess we're going to have a break now, and then we'll reconvene at 5 p.m. at the usual Melbourne, Sydney time. So so see everybody then. I'm going to stop recording. I forgot to do.